Few seconds. Okay. Hello, everyone. I'm Maura Pintor from University of Cagliari. And today we have another event for our machine learning security series. Today we have as invited speaker Francesco Croce, and we will tell you more about him and about his talk later. But right before we start, a few information for the event. First, the event is live streamed and recorded. So if you don't want to be live streamed and recorded, you can join from YouTube channel and it will be completely fine. Also because you can ask questions either on the Zoom call directly, raising your hand also during Francesco's talk, or by typing in the chat, and this will be given top priority at the end of the event. The Zoom call will have priority, and then from YouTube we will check if there are questions in the chat at the end. Moreover, if you want to have updates on new events that we organize, follow us either on Eventbrite, Twitter, or LinkedIn to receive our updates on the new events. And finally, if you are interested in machine learning security and you want to learn more about the basics, we also have a free YouTube course in the same YouTube channel as this streaming. So if you want to know more about the basics or more about other topics that are covered in machine learning security, then feel free to check out the course on the YouTube channel. And lastly, let me thank all people that helped me organize this seminar. And now I give the stage to Ambra, who will present our speaker.
Good morning to everybody. I'm happy to present our speaker, which is Francesco Croce. He's a PhD student in the machine learning group at the University of Tübingen in Germany. He received his bachelor degree in mathematics for finance and insurance, and his master degree in mathematics from the University of Torino in Italy. His research focuses on adversarial attack in different threat models and provable robustness. His talk today is entitled Toward Standardized and Accurate Evaluation of Robustness of Image Classifier Against Adversarial Attack. Francesco, the stage is yours.
Yeah, thanks a lot for the introduction, for inviting me here today. So I will share the screen. Yeah, you should see it now, right?
Yes.
Okay. Yeah. So I will just start. Yeah, so today I want to talk a bit about like how we can and when we can standardize the evaluation of the robustness of image classifiers against adversarial attacks. And so what I'm presenting today is based on some joint work with several coders, in particular Mattias Hein, Maxim Andriushchenko, Vikash Sevag, Edoardo De Benedetti, Sven Goval, Thomas Brunner, Evan Schlammer, Nicolas Flammarion, Pratek Mittal, Moon Chang, and Taran Chenjil. So first, like a very quick context, because I think everybody is familiar with the topic. So we have, our problem is that we have image classifiers which are very good in their task, but are vulnerable to adversarial perturbations. This means that if we have an image like on the one on the left, which is correctly classified, and then we had some small perturbation, and in this case, so in this example, actually perturbation is even very sparse, so the gray part is actually doesn't actually change the image, and we get another one which is most people would say identical to the first one. Now the classifier actually is wrong on this image. Okay, and there are like two main approaches to this problem. And the one is that of adversarial attacks, which try to generate actually these subtle perturbations. and the other side is that of some defenses which actually try to improve the robustness of the models. Okay, so the first one is about motivation of this line of work, and the question is why we actually need some adversarial robustness benchmark, and how can it be helpful. So first, we have a lot of works recently on defenses. So many defenses appear, and it's quite difficult to keep track of all of them, and especially to know which ones are the best performing ones. So, for example, we have this curve from Nicolas Carlini's webpage, which shows that in the last few years, thousands of papers have appeared about robustness, right? Clearly, not all of them are about attacks or defenses, right? But this just gives an idea of the trend in the field. Okay, and the second motivation is that actually evaluating adversarial robustness is not a simple task, and there are several examples where there have been an overestimation of the actual robustness. And finally, adaptive attacks are a potential solution for actually estimating properly or accurately robustness, but there are only approximated guidelines about how to create them, and this might lead to the fact that the results on different models are actually not comparable. So our goal here is to have a standardized adversarial robustness benchmark. And now, which are the ingredients we need to build such a benchmark? Well, first we need some standardized evaluation protocol through which we can get an accurate adversarial robustness evaluation. And this to be helpful, right? This has to work across classifiers, datasets, and threat models. So let's say LP norms. And then we want also to integrate adaptive attacks, which can be more expensive to create and to run, but might improve the standardized evaluation. And then we want also to have some restrictions on the allowed classifiers. In this way, we want actually just to rule out methods which actually make the standard attacks fail, but they not improve robustness. And then finally, we want to have a benchmark which is useful, and so we want it to be well defined and consider commonly used threat models. And we've kind of tried to follow these principles to design a robust bench. So, okay, as I said, the goal is to track the progress of the very robust models in a standardized way. And there are like three main parts in this project. And okay, first, clearly it's the leaderboard. So we have the evaluations of the most effective defenses under our standardized protocol. And at the moment we have 150 plus entries and different threat models. Then we want also to collect these robust models to make them easily accessible to everybody. And then we created this model zoo, and with like 120 plus models, but this is growing. And finally, since we have collected all these results and all these classifiers, now it's kind of easier to actually provide some analysis about some different aspects of robust models. So we have different trends, and we can evaluate also robust models in other metrics like calibration, fairness, and privacy, and to see how actually they behave there. Okay, now we'll go just quickly through the main components of robust bench. And okay, the first one is the leaderboard, right? And as datasets, we choose, so we focus on image classification tasks. So we have the most commonly used datasets such as Cypher 10, Cypher 100, and ImageNet. And also the threat models are clearly the most popular ones. So we have Infinity and the two bounded adversarial perturbations, which are kind of the most well studied. and where the attacker can craft perturbations which have some limited norm in L1, so L infinity respectively L2. And we also had like common corruptions from Index et al. And some examples are given in the figure, which are not actually adversarial perturbations in the sense that they are like a fixed set of perturbations applied to images. But these are clearly of interest for a more general idea of robustness, and these are kind of the first step to go toward like other threat models, for example, adversarial corruptions, which are kind of not super established yet, but maybe at some point in the future. Okay, in the table there's like a snapshot of how many evaluations and models we have in Robust Bench. Actually, this is kind of a bit older because it's taken from when the paper was published, but since then both have been growing. Okay, so how do we evaluate robustness? Well, for common corruption, it's quite easy, right? Because it's not an adversarial evaluation, it's just an average case. So we can just compute the average accuracy on the fixed test set, and we have 15 common corruption types and 5 severity levels, and we compute the average across all of them. For LP bounded threat models, instead we use as a standardized protocol auto attack, which is kind of an ensemble of white and black box attacks, and then we integrate external and adaptive attacks to track the most accurate evaluation available. And we invite also like people to submit not only models on Robust Bench, but also evaluations. And we also added a flag and to signal that the standardized evaluation might be unreliable. And so this flag is triggered when the black box square attack, which is part of auto attack, actually improves significantly the robustness compared to the evaluation of the white box methods only. This is kind of like a rule of thumb to decide when there is some kind of gradient obfuscation problem or similar, right? So, and we use it like to kind of flag that there might be the need. Actually, there is the need of some further evaluation. Okay, so now we have evaluation. Now we want also to have some. We need actually some restrictions to make this standardized evaluation to work properly. Okay, the goal, as I said earlier, is to rule out methods which actually do not allow the standard methods standard attacks to work properly, but they don't actually improve robustness. So this means that we accept only models that have, in general, non-zero gradients with respect to the input. So, for example, we exclude defenses which have a quantization of the input. Then we accept models which have deterministic forward pass, so no randomization, because this might require kind of things like EOT like stuff. And so it's a bit harder to standardize. And finally, we don't accept the models which have an optimization loop in the forward pass. So like test time defenses or methods based on the projection through some GAN data approximation of the data manifold and so on. And the problematic part in this case is that it's very hard. So usually these optimization loops are not differentiable. Then standard attacks actually do not work or not work in the standard way. But of course, these are kind of like a picture of the moment of the field. because we would be happy to actually lift some of these restrictions if it's some standardized evaluation methods will come up at some point. Okay, now, well, finally, this is kind of how actually the leaderboard looks like. And we have, okay, this is kind of for Cypher 10 and an infinite threat model with budget 8/255, so the standard, the most popular threat model. And okay, for each entry we have method, we have standard accuracy, robust accuracy given by the standardized evaluation, so by out attack. And then we have the best known robust accuracy, which involves also external or adaptive evaluations, our flag, so whether or not our flag has been raised, and then extra data and architecture, which are kind of two major factors which influence robustness. So extra data is shown to improve a lot, right? Robustness, and the same thing for larger architectures. So generally speaking, larger architectures lead to better robustness. So we want kind of to ablate the effects of these two factors. Okay, and of course we welcome submissions of new models. Okay, now the second component of Robust Bench is the model zoom, and well, the goal is actually to just give simple and unified access to the most robust classifiers, and this can be done with a couple of lines of code. The model zoom can be useful because it can be exploited for new research, so in different ways, for example, as meta-analysis or fine-tuning, or just as an accessible source of strong baselines. And we also give the option of quickly benchmark new models with some very simple 2 lines of code. Oh, okay. And now the last part of the Robust Bench project is to actually, since we have all these evaluations and models, we want to actually to learn something about the development of robustness over time, or other measuring how robust models perform in other metrics. Okay, so here are some examples. These are just given some plots, which can be actually reproduced with the data of the leaderboards. And we have for example, progress over time. So how robustness is going over conferences in this case. Then the second plot in the middle is about how is the evaluation of out-attack compared to the original one. And so we see that for some cases where out-attack improves a lot, the original evaluation, but there are a lot of cases where actually they are quite on the diagonal. So it's very close, right? Okay, and finally, what I mentioned earlier, right? We have a kind of a confirmation that extra data helps. So the orange dots actually have better both standard accuracy and robust accuracy compared to models without extra data, which are the blue ones. Okay. Now we can go a bit beyond and check how the robustness influences other metrics. And for example, here we have calibration, and basically we computed the expected calibration error, and we plotted against robustness, right? So we see that actually the robust models are not very well calibrated, even after temperature scaling, and compared to the clean model, right? Which is this dot with the 0% of robustness. And so the second example is about privacy leakage. So here the task is to infer whether or not some data belongs to the training set. At some point it belongs to the training set. And here instead it seems that actually there is no, so the robust models do not tend to leak more the training data, so they are kind of at the same level of robust ones. So, and there is no clear trend about robustness versus privacy leakage. Okay, these are just two examples, and we have actually other analysis about like performance on distribution sheets, or D detection, fairness, smoothness, and transferability. So, okay, this was kind of what we have so far, right? And now we can ask ourselves, how can we extend the benchmark, right? So the first thing and the easiest one probably is to include new threat models. And for example, there are like sparse attacks or adversarial corruptions, which I mentioned earlier, perceptual attacks and so on, and even datasets. So second possibility is to actually adding leaderboards for like separated from the current ones, but for other types of defenses, for example, detection methods. And so this work mentioned here from McLeod 2022 actually proposes kind of a standard, more or less standardized evaluation of detection methods. So this is kind of a candidate to become a part of a leaderboard. So finally, we would like actually to relax the restrictions on the models which we allow in the leaderboard side. And okay, what do we need for this is clearly to extend the benchmark is actually a standardized evaluation first, and then a good amount of models, because if there are no not enough actually classifiers on a given threat model, it's like less interesting to actually have having a leaderboard is less interesting. So the first thing we consider is that a new threat model. And okay, this is kind of probably one of the most natural ones. So we have L2 and L infinity, and now we want to extend basically auto attack to the to L1 bounded perturbations. And okay, the main novelty is given by extending ABGD. Okay, in general, we have PGD-based attacks, which aim at solving an optimization problem like this one. So we want to maximize some loss, which is kind of which induces misclassification, and we want to have as constraints to be to use perturbations with L1 norms smaller than a threshold epsilon. And then we have to stay within the image domain 0, 1 to D. Okay, PGD-based attacks are kind of quite a simple scheme, iterative scheme, which consists in a first gradient step, right? When we update the current iterate with some function of the gradient of the loss, and then we project back to the feasible set if necessary. Okay, one note is that while for L infinity and the two threat models, we have some standard forms of PGD. This is not the case for L1. And the existing ones actually are less effective than other methods, so which are not based on projected gradient descent. Okay, so what we do here is that we want to consider actually in L1 the role of the image domain 0, 1 to the D, which is kind of a bit overlooked in the other threat models. So first, the first component of the scheme of PGD is the projection step, and we want to here we want to project on the intersection of the L1 ball of radius epsilon. So basically, this first constraint, and then end of the image box 0, 1 actually. so at the same time, right? So the intersection of these two sets. And existing versions of PhD for L1 actually just project first onto the L1 ball and then clip to the 0, 1 box, but this is not the exact projection, but just an approximated one. And like in the figure, we can see, like on the left, actually an L1 ball in 3D, right? An example 3D, an L1 ball versus an L1 ball intersected with the box. And this shows that actually the feasible set is quite different, right? Like considering the box or not. Mainly we show that actually the projection problem onto the intersection of ball and box can be solved in the same time as just a projection on the ball, on the one ball, and in particular in DWD time. And also that actually the exact projection allows to better explore the feasible set compared to the approximated one, which leads to stronger attacks. So basically, this projection is actually an important component for the success of the attack. Okay, a second part of the iterative scheme is the update step. So, and in the PGD-based attacks, we use commonly the steepest descent direction for threat models, for the particular threat models, and which is defined in our case as the direction which maximizes the linear function inside the feasible set. And so we show that actually the main point is that this can be solved for our problem, right? Exactly. And the sparsity of the steepest descent direction depends actually on the current point, so the point x in this case. And so basically differently from the current methods or the current versions of PhD for L1, which use actually updates with either fixed or random sparsity. We use in our L1 PhD updates with adaptive sparsity. In particular, the rule according to which we adapt the sparsity is the one in the equation, the last equation. And the idea is that we start with the low sparsity, so that we basically explore quickly the feasible set, and then we adjust every m steps according to the rule, which basically says that we take the current sparsity of the current best perturbation found, so the one corresponding to the highest loss, and we reduce it a bit, right? So because we are starting from high, so low sparsity, and we want to get to actually go to a higher sparsity, and depending on the solutions we find. And similarly, we want to also to adapt the step size of like for the gradient step, right? How we do it? So, well, the idea is the formula maybe is a bit complicated, but the idea is quite simple. So, if the sparsity doesn't increase, so basically, we have kind of found the let's say the exact sparsity of our final perturbations, or a good approximation of it. Then we reduce the step size, so we make approximation, so optimization more local. Otherwise, we reset the step size to a large value because it means we have reduced, so increased sparsity, and then we are exploring kind of a different region of the feasible set. So we want again to take large steps to explore it quickly. Okay, and the final like change we do to the PGD scheme for L1 is we want to find good starting points. To do this, actually, we split the total budget of iterations into 3 phases. And we start with in the first phase we use as bound on as constraints on the L1 norm 3 times epsilon, and the second 2 times epsilon. Just in the final one we use actually epsilon, which is kind of our final threat model. So the true threat model is actually used just in the last phase, but in this way, using larger ones, we actually are able to find better starting points for the next phases, right? So the output of each phase is used as starting point for the next one, and then this improves optimization. Okay. So here's some results, right? And here in particular we have the comparison of our L1 PhD to other PhD versions, and so in the in the top two plot we show that we show loss and robust accuracy of each method with the exact projection, so with the solid line, and the approximated projection, so L1 plus clipping, and we see that basically all methods improve loss and improve robust accuracy when using the exact projection. And yeah, so in this case, robust accuracy, so lower robust accuracy means better, like stronger attack. And then in both cases, so for both cases, we see that also L1 PhD achieves like higher loss and lower robust accuracy, so outperforms the existing versions of PhD, and both with the standard L1 PhD, so just a single value for epsilon, and also for like what I mentioned last, so about multiple values of epsilon. And finally, we want to show also the adaptiveness of L1 PhD to the budget of iterations. And this is done kind of in the bottom two plots. So, and here we have just a single epsilon PhD with a different number of iterations. And what we show is that basically, if we have more iterations available, the optimization actually goes like slower at the beginning because there is more exploration of the feasible set, but then it starts growing with the progression of iterations, and in the end achieves higher values of the loss than with a lower budget, right? And the same works for the robust accuracy. Okay. Yeah, finally, we want to adapt. So in auto attack, there is also square attack, which is a black box version attack based on random search. And we just adapted to the L1 case with basically integrating the projection onto our feasible set. So in the intersection of L1 ball and 0-1 box. So this is kind of a minimal change box. And okay, we showed also with some results. Basically, we tested so different attacks on like a lot of models. Some robust for L1, some for L2, some for infinity, some for multiple norms. And we see that with this is just with a single run, and epsilon is equal to 12 and cipher 10 with these values. So and APG works pretty well. And also, so the last two columns are about black box attacks. And so we see that also L1 square attack works better than existing method. Okay, basically now these are kind of the two missing ingredients for auto attack, to have a version of auto attack for L1. And so now that we have it, we can like compare it and to see on different models. Basically, models are the same as before, and we just use the auto attack and we compare it to the like WC is the kind of the worst case across all the attacks which are not included in auto attack. So quite a large set, like larger than the set of attacks in auto attack. And we see that in most of the cases it gives the best evaluation, and okay, in some cases does not, but it's very close, right? So we want to have kind of a close to best evaluation, so it's still accurate. Okay, and as another like note, we use also APHD, L1 APHD for adversarial training, right? And this actually gives a very high, so it's very effective. It's very high robustness, like robustness in L1. So for L1 adversarial training. Okay, so this was like a first possible extension of Robust Bench to a new threat model. And so the second option would be to extend it to a new data set, right? And okay, it's kind of natural to think about ImagineNet because it's like super common. But so in this case, we have like a problem that actually there are not many robust models on ImagineNet. Because of like it's a super large data set and with quite a high image resolution, right? So standard is like 224 times 224, so which is like orders of magnitude larger than Cypher 10, Cypher 100. Okay, and and the problem is that okay, training models on ImagineNet is like quite expensive already with the natural training, and it becomes clearly much more expensive with adversarial training, which is kind of the best defense at the moment for Cypher 10, Cypher 100. And even like experimenting with it is kind of infeasible, right? Because we cannot train hundreds of models in a short time. And this problem is to some extent can be also seen on Cypher 10 scale, because like the latest updates, like the most recent methods for on Cypher 10, which achieve the best results, are with the very, very large models, right? So which are kind of again quite expensive to train. So the idea is actually to not training from scratch every time to have adversarial robust models, but to use just some quick fine tuning with adversarial training. So the idea is we take just one existing robust models with respect to LP, and we actually make it robust to another threat model, in particular in this case LQ, so with the Q different from P, or even from multiple non-robustness. And like the figure summarizes a bit the results in Cypher 10, so like a subset of the results. And basically, if we take in the center, there are statistics for one of the most robust models for L infinity. And this is kind of a wide result 7016, so quite large. And we took like this was trained with hundreds of epochs of training, and basically has initially no L1 robustness, and we fine-tune for just 3 epochs with adversarial training for L1 to achieve L1 state-of-the-art L1 robustness, right? And clearly the L infinity goes down, right? Because we emphasize L1, we lose in other like categories. And we can do the same with multiple norms. So basically, this is kind of with 3 epochs of EAT is just like a version of the style training we introduced for multiple norms. So basically, we just do adversarial training with L infinity and L1s, kind of the extreme norms, and this is enough to actually achieve robustness also for the intermediate ones. And here the goal is actually to improve the union. Okay, the union robustness in the union is just the worst case over L infinity L2 L1. And we see that with this just quick fine tuning, we actually achieve very good robustness. So still the robustness for multiple nodes. And okay, this is basically is achieved with a very large model, but the main point is that we didn't need to retrain the whole model, but we just used an existing one. Okay, now actually on ImagineNet, right? Since this is kind of the main motivation, we just do 1 epoch, because as I said, the training set of ImagineNet is quite large. And we fine tune either either ResNet or a vision transformer. Actually, this works also for gauges, and we can obtain models robust. We start with models robust with just in one LP norm, so either infinity or L2. And then we fine tune to other norms. For example, like here on the right, there is from one for either L infinity or L2 robust models to individual norms. And so L1, L2, and L infinity. And this is sufficient, right? One epoch is sufficient to get quite a high robustness in the target threat model, and the same in bottom part of for multiple norms fine tuning. So fine tuning to have robustness in the union. And here, basically, we start most of the models actually like a zero, very close robustness in the union, with this short fine tuning. Actually, we achieve quite some improvement, and with little cost. Okay, this was kind of a possible approach to extend to have more models on more datasets and on in more threat models, right? So to have quickly more like a higher number of robust classifiers. Okay, and finally, yeah, we want to have a look. So this is kind of the last part. We want to have a look of what happens beyond the restrictions, right? So which methods are we actually excluding when we impose such restrictions? And so we start analyzing some subset of all the possible ones, and in particular we focus on adaptive test time defenses. And okay, basically this means defenses which actually have an optimization loop in the forward pass. And in particular, the main principles of these defenses are either input purification. So basically, the model receives an input which might or might not be adversarial, and there is some process which purifies it, and basically the idea is to remove the adversarial noise. And the other principle is model adaptation, which actually the model itself modifies its weights depending on the input. Okay, and how these principles are realized through these a few main building blocks. And okay, common to all of them is some iterative algorithm, so which are usually gradient-based optimization methods, but there might be also like implicit layers. So for example, this, like neural ODE blocks, or like recurrent layers. And oftentimes there are also auxiliary networks are used, especially for the purification. And then many of these defenses actually rely on randomness. And finally, some of them actually use some external data for inference, which means that, yeah, the output of the classifier doesn't depend only on the input or the simple input, but there are also some other sources of uncertainty. And okay, when it comes to evaluating these adaptive test time defenses, there might be some obstacles, and it might be difficult, especially because of like, okay, the gradient obfuscation, in the sense that okay, so there are several causes of this. For example, there are like non-differentiable components, and this is quite problematic. Or we have some since we have some iterative schemes, there might be vanishing or exploding gradients. So yeah, the gradient information might be kind of not easy to use. Then there is randomness, right, which clearly makes things more complicated. Also one like maybe a bit less clear obstacle is the increased runtime. So since there is this optimization at test time, so at inference, for inference, this costs some computations and time. So it's like even running attacks takes much longer, and this has to be considered actually even for clean inference, because this is kind of several times more expensive. Can be several times more expensive than for feed-forward models. Okay, and we took like a few existing methods, and we kind of tried to evaluate the robustness. And okay, the results are in the table. And so maybe just to the table. So the main results about robustness are in the last three columns. And okay, the reported robustness is quite clear. And in our evaluation, we have we report. So the second column is like the final robustness, and the third column in brackets is the robustness of the basically underlying static classifier. So if we don't have any test time difference, basically. Right. So some of them are kind of clearly robust models, so some of them are non-robust models, but so this is what we would get without any optimization at test time. So like our observations are that to evaluate to get a strong evaluation of for these defenses, actually you need to combine different existing techniques. For example, like we have combined several times the APG with the BPDA, which is kind of a way to approximate non-differentiable components. And then you might or might not include also EOT or like transfer attacks. So basically, these are all existing methods, right? But just combined in a suitable way. And and the other observation is that actually at the moment, well, adaptive test time defenses do not outperform static ones. So basically, adversarial training. But like the main one important observation is that actually we couldn't find a standardized protocol for evaluating these defenses, right? So as you can see, like the evaluation method, basically there are a lot of different things, and it's quite hard to standardize this. So probably it's not easy, right, to lift the restrictions from a robust bench-like benchmark for adaptive test time defenses. Oh, okay, no. Okay, so basically this was it. So like these conclusions. So we see that it's possible actually to have a standardized benchmark for cell robustness, but we need some conditions, and we have to some restrictions on the models, and we need some evaluation. But actually this might be useful because we can actually track progress and to use actually these robust models for something else. And yeah, we want to clearly expand, right, the benchmark in different directions. And of course, this is possible if there are like sufficient, so good standardized evaluation, sufficiently many models, and in the end, like the interest of the community in these models. Okay, thanks a lot for the attention, and like I'll be happy to answer questions.
Thanks a lot for the talk. Any question from the audience? It seems there are no questions now, so let me start with a question.
Yeah.
You said, I mean, considering the first bulk of models, so when you exclude, for example, models which have a non-deterministic forward pass, okay, you said that you have a flag, okay, to basically understand when an adaptive evaluation is needed. Okay, so that's more a curiosity than a question, but is since when you started with the leaderboard, how many flags you have seen?
Okay.
Lots, few. Can you tell something more about this and which were the problem?
So actually, this I can say easily. So at the moment there are just 2 models with this flag, and one model is quite like we had initially, right? The problem is that like the input, like the lost landscape, the input space is super non-smooth, so it's you get like super noisy gradients. And there, yeah, a black box method actually works best. And the second one is actually one we had recently. So this is a model with based on a neural OD block, right? So which has kind of a layer which uses some like a numerical method to solve an OD. Yeah, apparently so these are models are quite rare, right? So we my knowledge. Apparently gradient-based methods are kind of not working super well. So it seems to be some problem with like having meaningful gradients. If you just these models are completely differentiable, right? But the problem is that there are some issues with computing the gradient and about how informative the gradients are, and so it seems that like the black box method still improved a lot in evaluation. So yeah, this is kind of the second case. Yeah, at the moment there are just these 2.
Okay, thank you. I see a raised hand from Jérôme. So Jérôme, please go.
Thanks for the presentation. I wanted to have your opinion on the current robustness evaluation situation where people basically evaluate one epsilon, basically. Like for CIFAR, it's 8/255. For ImageNet, I think it's 4. Do you think there should be an effort to actually like extend that to more sizes? Because to me, it seems like you could, like in a way, optimize for that specific step size and maybe miss like the more global picture of being robust.
Yeah, that's so definitely it's true that I mean these thresholds are quite arbitrary, and it's not clear. Like I mean, okay, I guess they were chosen because of images are still imperceivable, so the perturbations are still imperceivable mostly, and yeah, it made sense. But it was not trivial to get robustness at that levels. At those levels, I think like if the goal is like a leaderboard, it's much easier with a standard threshold because it's super easy to compare, and it's not necessarily the case for multiple like epsilons. Yeah, so for example, okay, one thought is that for example, L2, right? We now have 0.5. We are kind of robust accuracy is approaching clean accuracy. So probably it's not challenging anymore. So we should maybe go over if it's possible. Go over so I mean, going towards something larger. Yeah. So I think it's not clear why having a fixed threshold should be better. But at the same time, it's an easier task, right? A better defined task, especially for adversarial training, right? You want to have a threshold so that you can optimize whatever you want within that feasible set and so on. I mean, in general, I think we are going toward more like a generic or general idea of robustness. So we will probably at some point like kind of like to cover thresholds, not just for LP norms. well, for other threat models. So yeah, I don't know if this is an answer, right?
Yeah, it's more of an open question, really. But it's do you think that maybe like we would need maybe like new metrics to evaluate robustness? And because you said to compare on a leaderboard that it's easier at a specific threshold, but yeah, in my opinion, like a specific threshold doesn't give the full picture. So maybe there would be a need to have like more general metrics than just accuracy at one threshold.
Yeah, no, that's true. I agree that it's not a general, like it's not a comprehensive metric. But okay, I think the solution is not really to have like more thresholds, right? So I mean, I guess we don't want to have another leaderboard for like 12 over 255 because it's just like repeating the same thing. I think if it's possible to have like a metric which like encapsulates like all the threshold, like average distance to decision boundary or something like this, would definitely be interesting. So most of the works that we focused on this fixed threshold robustness, right? Especially for the defenses, because the attacks, I think you can always kind of adapt it, right? But like if you look at the like methods for as adversarial training, there have been some attempts to improve point-wise robustness, right? So not having a fixed threshold, but depending on the point itself, having larger or smaller thresholds. It's just more complicated to evaluate to define this.
For me, well, I'll end here, but for me, like it's the same situation as where you evaluate a binary classifier, for instance. It could be multi-class, it's the same thing, but like if you evaluate that the threshold of 0.5, it's not like it doesn't give you the full picture, and then people use ROC curve or PR curves because and you compute an area, and like I believe you could do the same kind of analysis for robustness, but yeah, that's my opinion.
I mean, it would be possible. Yeah, sure. Yeah.
Thanks.
Okay, we have time for one question. I see a raise hand from Battista Biggio. So Battista, please.
Hi, thanks. I would just want to do a quick follow-up on what Jerome was saying. Because first of all, I want to congratulate with Francesco and his colleagues for setting up all this leaderboard and the benchmark, which I think is helping us to make progress in this field. But I'm also having the impression now that people start to overfit the benchmarks, you know, as it happens. If you get like 1 or 2 points more in robustness, is this real progress or not? So, and how do we get to know this? And in this sense, I think that Jerome has a good point that if you just consider 1 epsilon, this is maybe you're not giving the full picture because perhaps, so it's good to measure that, but it's also good to see how gracefully the robust accuracy decreases when epsilon changes. Because you may get something which is very robust at that specific epsilon, but it's useless if then if you do epsilon plus another small epsilon, then if the performance drops immediately, then it's not really robust. So I think to make real progress, we should have algorithms that in the end show a graceful decrease of performance with respect to an increase in the perturbation sites and not like an abrupt change as soon as you are, instead of 8 over 255, 9 over 255. So I don't know if the question is clear, but I think it's more in the sense of sensitivity to perturbation.
No, the question is clear, I guess. So about overfitting to the leaderboard, so to some extent it's possible, right? I mean, it's clear that if it's a well-defined target, right? So, and you want to optimize there. And I don't know if, I mean, I guess any progress is meaningful, right? There, clearly, so you can get progress by just adding making a model a bit wider or deeper, and that's it, right? Training it for longer, and this is kind of probably not super interesting, but if you have some algorithmic progress, right, that's also the algorithm improvement, then it matters, even if you're improved just like 0.1%. About like the curves, sure. You we would like to have something which is kind of which generalizes right over the thresholds, so beyond thresholds. So in this case, so in the case of the leaderboard, right, I meant so we have to define like a metric, right? We want to optimize. Otherwise, it's just so oftentimes, right? There is the comparison between. Okay, maybe this is an example, right? Of okay, there are methods which so there is this trade-off between clean and robust accuracy, and there are methods to mitigate this. And it's super difficult, at least for me, to judge this, because you have two metrics which are not really comparable. Like you can take an average, but is 1% of robustness worth 1% of clean accuracy, or like something like this, right? So it's not a very well defined metric. So I think like a benchmark for this is possible once we define a metric to optimize. Yeah, and then we can measure it, because so the moment I guess we could just do it through curves, right? Okay, yeah, as Jerome said, some AUC heating, or but yeah, I think at some point we really want to threshold the right things. For example, if we talk about, okay, maybe the link fit is less important, but for L2, for example, at some point we want to not be robust, because there are some examples which, if you go too far in some specific direction, right, you actually change the class. So you don't want to be robust there. And this is super hard to define. And this is point-wise also. So I think it becomes quickly quite hard to have a good oversight of everything. I hope this answers kind of your question.
Yeah, thank you.
Sure.
Thank you. I think we are running out of time, so thanks again for the talk, and I leave the stage to Maura, which will conclude.
Yes, thank you, Ambra, and most of all, thank you, Francesco, first of all, because you're trying to and also managing to optimize, to promote open research and also standardizing this kind of evaluations. And also thank you for the great talk. I really enjoyed it.
Thanks for the invitation.
Thank you.